The universe is filled with energy, containing objects having least possible amount of energy, as well as gigantic powerful objects that release enormous amount of energies. Considering the huge size of the universe, in it containing billions of galaxies, each galaxy containing billions or even trillions of stars, and each star utilizing fusion to generate energy for billions of years, it's only rational to imagine that the total amount of energy in our universe should add up to an unimaginably large number. Well, it doesn't. The total amount of energy of the entire universe is 0. What? In the previous episode, we mentioned that in quantum theory, nothing is described as fundamental energy fields. The combinations of these energy fields is also called the quantum foam, the substratum of all existence. It's the smallest quantum reality available everywhere. And by everywhere, I mean literally everywhere, even in intergalactic space between galaxies. Quantum foam is filled with potentiality, having a non-zero value and always jittering without rest, generating fluctuations known as quantum fluctuations at an unbelievably small scale called Planck scale, which is about 10 to the power of -35 meters. At this incredibly small size, space is no longer the ordinary smooth space we recognize. At this scale, space becomes foamy, a chaotic entity consisting of bubbles. That's why the smallest quantum reality is called quantum foam. According to some hypotheses, which we'll get into shortly, quantum fluctuations give rise to literally everything we perceive as existence, making them as fascinating as one can comprehend. You can think of the quantum foam as a fizzy root beer. In terms of fields, the non-zero energy variations are called quantum fluctuations, and in terms of particles, they're called virtual particles. The reason why they are referred to as virtual is because they don't exist as observable entities, but their existence is measurable. They are also temporary, meaning they are present during calculations, but can't be detected as single particles. Virtual particles are constantly popping into existence by borrowing energy from quantum foam, live for a very short period of time, and then annihilate each other and return to borrowed energy. Like electron fields giving rise to electrons, quark fields giving rise to quarks, and so forth. However, that short period of time is enough for virtual particles to leave measurable effects. Since they can interact with real particles, virtual particles are an essential part of quantum mechanics and are extremely well tested, and this has allowed scientists to understand their quantum mechanical consequences. A great number of experimental measurements demonstrate that virtual particles do exist. The effects of quantum foam can be experimentally observed in various phenomena such as CASMIR effect. If quantum foam really exists, the virtual particles should be everywhere. And since particles have particle-wave duality in their nature, we should be able to detect them as waves everywhere. So if you place two parallel metal plates near each other, quantum foam would exist between those plates as well as outside of them. Putting plates close to each other results in only short waves to exist among the plates and longer waves to exist in its exterior, which creates an imbalance. This imbalance will eventually push these two plates closer to each other. The CASMIR effect was first measured in 1958 with many experimental errors, but then measured more accurately in 1997. If scientists want to ignore the fact that quantum fluctuations really exist with their associated energy, they should also be able to explain the many experimented and proven results. They have concluded that quantum fluctuations happen everywhere all the time. the energy levels of atoms are being directly affected by virtual particles. Without considering quantum fluctuations, different predictions regarding energy levels will be in disagreement with the experimentally measured levels, so quantum fluctuations should be taken into account. Quantum mechanics demands temporary creation of virtual particles, which then immediately join and then cancel each other out so fast as if they had never been there in the first place. At first glance, these energy appearances seem to contradict the basic principle of physics called energy conservation. According to Einstein's famous equation, E equals mc squared, energy converts into matter and vice versa. The energy of a closed system is conserved, and it can't be created nor destroyed. According to current understanding, energy isn't necessarily conserved globally, but it is conserved locally. So how could it be that quantum fluctuations arise from the energy field without violating the energy conservation? Well, there's a loophole. The appearance and disappearance of virtual particles happen in a time scale shorter than mankind can ever hope to measure, called Planck time, which is about 10 to the power of negative 44 seconds. The relationship between energy appearances and time is explained in a principle called Heisenberg's uncertainty principle. According to this principle, in the case of virtual particles, a temporary violation of energy conservation is allowed as long as particle appearances and disappearances are happening in a time scale shorter than Planck time. You can also say that energy conservation is not a violation at all, since the fluctuations occurred in a time shorter than Planck time. It's like cheating in a card game by quickly flipping a card and taking a quick look at it without your opponent noticing. There's no reason for the game not to continue, since from your opponent's perspective, no rules have been broken. Imagine these two cases. 1. You have no money. And 2. You borrow $10,000 from a friend. In both cases, you don't own any amount of money. In second case, you do have $10,000, but that money isn't actually yours and should eventually be returned. The difference is that in the second example, you can do some interesting things with that borrowed money. Let's say, start a small business. That's how virtual particles borrow energy and come into existence. It's been proposed that quantum fluctuations might have existed before our universe. In fact, according to this hypothesis, quantum fluctuations gave birth to our universe. This hypothesis was originated by Edward Tyron in 1973, suggesting that the universe is the result of quantum fluctuations. Our universe is filled with matter, antimatter, and radiation, distributed everywhere. And yet, the total and fixed energy of the universe is 0, because there's also an equal amount of negative gravitational energy distributed between all the positive energy particles. As Stephen Hawking mentioned in his book, The Theory of Everything, The Origin and Fate of the Universe, the matter in the universe is made out of positive energy. However, the matter is all attracting itself by gravity. Two pieces of matter that are close to each other have less energy than the same two pieces a long way apart. This is because you have to expend energy to separate them. You have to pull against gravitational force attracting them together. Thus, in a sense, the gravitational field has negative energy. In the case of the whole universe, one can show that this negative gravitational energy exactly cancels the positive energy of the matter. So the total energy of the universe is 0. In the case of dark energy, the repulsive force responsible for the expansion of the universe, Hawking continues to say that twice 0 is also 0. Thus, the universe can double the amount of positive matter energy and also double the negative gravitational energy without violation of the conservation of energy. This does not happen in the normal expansion of the universe, in which the matter energy density goes down as the universe gets bigger. We'll cover the dark energy in full detail on future episodes. If one combines everything at the beginning, in its current date, or even in the future of the entire universe, the sum must always be 0. The virtual particles rising from quantum foam are particle and antiparticle pairs, colliding with each other and disappearing. This event can be described as the following: 0 equals +1 plus -1. 0 represents the quantum foam. +1 and -1 represent a particle and antiparticle pair, which cancel out and become 0. Same goes for our universe. +1 is the positive energy, meaning matter. -1 is the negative energy, meaning the gravitational energy, which leaves us with 0. They appear in pairs basically because for every +1, there should be a -1. The charge conservation can't be violated, and that's why these particles appear in pairs, so their charges will cancel out to 0. So if we cancel out all the positive and negative energy in the universe, nothing would be left. If we imagine a bubble created by virtual particles, based on the zero energy universe hypothesis and as a rule of uncertainty principle, the relationship between the energy and the surviving time of that bubble goes as following. The lower the energy of the bubble, the longer it can survive. It's like when you charge your cell phone to full and do not use it much, causing the battery life to last for almost 2 days. But if you continuously use it by watching a video or surfing the web, the battery will be completely exhausted in just a matter of hours. That's how our universe borrowed this energy and came into existence. Time and energy do exchange in uncertainty principle. Due to the relationship between energy and momentum, if a universe starts with a large amount of energy, it's going to last for a short amount of time. But the low energy universe is allowed to exist for a very long time. Our universe has zero total energy, or an amount very close to zero, which allows the universe to exist for a very, very long time. The zero energy universe hypothesis allows a universe with a fixed zero energy to fluctuate into existence given that the universe is flat. Cancellation of positive and negative energies leads to a flat universe. Studying the shape of a universe is another way of examining its energy level. Einstein's general relativity shows that mass and energy bend the fabric of space-time, and it determines the type of curvature space-time has by representing a value called omega, the density parameter. If omega is larger than 1, there is positive curvature. If omega is less than 1, there is negative curvature. And if omega equals to 1, the universe is flat. Different experimental data from independent sources like WMAP, BOOMERANG, and PLANCK have confirmed that our observable universe is indeed flat with a 0.4% margin of error. We already saw that the universe has zero matter energy content, and the same goes for its charge and spin. According to the theoretical physicist Dr. Michio Kaku, if you calculate the total positive charge of the universe followed by its negative charge, it will add up to 0. The total charge must be cancelled out in a closed universe. Also, if you add all the spins of galaxies, which are spinning into different directions, the result would be 0. As a mathematical fact, the energy of a closed universe is 0, in which the positive energy of matter is being cancelled out by the negative energy of the gravitational field, so the total energy is 0. If all the conserved numbers of a closed universe add up to 0, then there is nothing to prevent such a universe from being spontaneously created. In quantum mechanics, any process that is not strictly forbidden by the conservation laws has a non-zero probability of happening at some point. Quantum laws might govern the entire existence and allow a universe to begin from nothing. Quantum mechanics implies that due to the uncertainty principle, there will always be fluctuations no matter what. Our flat universe with zero total energy could potentially have begun from random quantum fluctuations. If the zero energy universe hypothesis is correct, then we might be able to confirm that the universe came from quantum foam caused by its non-zero energy fluctuations. It has zero total energy, and yet it has a magnificent structure and complexity. If true, then there is no reason to not consider the fact that other universes are also being created probabilistically due to fluctuations, maybe for eternity. These are all based on scientific hypotheses and theories, but they are getting more and more sensible and acceptable as scientists make progress. Many problems in physics and cosmology remain for scientists to tackle with, and those problems are tough, which makes this whole thing much more interesting. Virtual particles appear and disappear for no reason, and since they are the originators of reality as the zero energy hypothesis suggests, then maybe it is reasonable to think that the universe also came into existence for no reason. If quantum fluctuations exist outside the universe with the same principles, then our existence is inevitable. Quantum fluctuations are manifestations of nothingness. It seems like nothingness wants to manifest itself by creating something all the time. So to conclude, our universe is a strange version of nothing. That's why the theoretical physicist Alan Guth refers to the universe as the ultimate free lunch. Or as Dr. Kaku says, the universe is for free. Thanks for watching. Don't forget to share and subscribe if you haven't yet, and stay curious.